Good afternoon, everyone. I'm Tian. Today I'm going to present our paper, Efficient and Precise Point Analysis, Modeling the Heap by Merging Equivalent Automata. I'm just received my PhD from University of New South Wales, and my supervisor is Jingling. And for this paper, both Yueli and me are co-first authors as we contribute to this paper equally. In this work, we propose a new points-to analysis technique for all programs. Points-to analysis determines which objects a variable can point to statically. As a fundamental analysis, it is not only used by many clients, but also implemented by many analysis tools. But maybe the most common use of points-to analysis is to build cographs. Currently, on-the-fly construction, which runs together with points-to analysis, may be the most widely used cograph construction because it is precise, but it can be inefficient. An example is to use three-object sensitive points-to analysis to build cograph. The analysis is very precise and adopted by many tools. And let's see its performance. We use the analysis provided by Duke, the state-of-the-art points-to analysis framework for Java. We use the machine with good performance, and time budget is 5 hours. We analyze these two popular Java applications. The analysis spans 4 hours to analyze PLDI, and is even unscalable within 5 hours for $5. We can see the precise points-to analysis is still slow. So what are the developments in points-to analysis during these years? In last decades, there are two main streams of points-to analysis techniques: modeling control flow and modeling data flow. For all programs, context sensitivity is the main technique to model control flow. Several different kinds of context sensitivity were proposed. As for modeling data flow, the representative technique is Heap abstraction. While context sensitivity received much attention, little progress was made on Heap abstraction. But in this work, we focus on Heap abstraction. What is Heap abstraction? In dynamic execution, the heap can be infinite size in case of the objects are created within loops or recursive methods. So to model such heap, static analysis applies heap abstraction to abstract the infinite size heap into finite abstract objects. A typical heap abstraction is allocation-site abstraction, which creates one object for each allocation site. So for this code, the allocation-site abstraction creates 3 objects, 1 object per allocation site. Here, the A at up right corner denotes to the type of this object. So this is an object of type A. Currently, allocation-site abstraction is predominantly used and adopted by all mainstream points-to analysis due to its good precision. But it has our partition problem for cograph construction, which affects its efficiency. Let's take a look at this example. Allocation-site abstraction creates 2 objects for these 2 allocation sites. Through these 2 method calls, both objects flow to method foo. So in points-to analysis, O points to both objects. But when we analyze this method code, its calling can only be A2 string. But allocation-site abstraction still creates 2 objects of type A. In worst case, in points-to analysis, O might point to hundreds or even thousands of objects of type A, which slow down the points-to analysis without changing the precision, because no matter 1 or 1,000 objects of type A pointed by O, they make no difference to the quality of this code site. It still can only be A2 string. Actually, our partition affects not only cograph construction, but also an important class of type-dependent clients, such as devirtualization, Mayfile casting, and so on. And the precision of these clients depend on the types of objects pointed by variables. For example, if we analyze whether this code can be devirtualized or whether this task may fail, we only need to know the types of objects pointed to by variable O. But for type-dependent clients, our partition problem can make precise point-to analysis very slow. Another typical type heap abstraction is type-based abstraction, which creates one object for each type. So for this code, type-based abstraction only creates two objects, one object per type. And this abstraction is more efficient than allocation-site abstraction because it creates less objects. But it will cause precision loss for type-dependent clients. For this example, type-based abstraction creates three objects for these four allocation sites. And in points to analysis, A1 and A2 point to OA, and B and C point to OB, OC, respectively. Through these two store statements and this load statement, finally O will point to OB and OC. As a result, cograph construction will report that this cosi has two polys. However, this coedge to C2 string is clearly a false positive because during the execution, O can only point to the objects of type B. The problem here is that type-based abstraction blindly merges objects of the same type without considering their heap structure, and this can easily cause precision loss, like this example shows. So given this background, our goal is to improve the efficiency of points to analysis while preserving the precision for type-dependent clients. We propose MAHONG, a new heap abstraction. And now let's preview its effectiveness. We compare MAHONG with the widely used allocation-site abstraction. When using allocation-site abstraction, the points to analysis spends 4 hours for PND and is unscalable within 5 hours for 5 bucks. But with MAHONG, the analysis times for these two programs are only about 100 and 500 seconds. So MAHONG hugely improves the efficiency. How about the precision? We evaluate the precision through the number of coregraph edges of PND generated by the points to analysis using these two abstractions. Usually, less coregraph edges means better precision. And we can see these numbers, they are exceptionally close, which means that MAHONG achieved almost the same precision as allocation-site abstraction. How do we achieve this? Our insight is that we know merge objects can alleviate our partition problem and improve efficiency. We also know that blindly merged objects will cause precision loss. The reason is that the types of objects pointed by the same field of the merged objects are inconsistent. And once such objects are merged, you will load more enforced types from the field access to the merged objects. For example, after merging O1 and O2 to OA, you will now load objects of type B and C from OA.F imprecisely because we know OB is false positive to the original O4.F and OC is false positive for original O1.F. So for this problem, we propose type-consistent objects. We say two objects, OI and OJ of the same type, are type-consistent objects if for every sequence of field names, say F bar, OI.F bar and OJ.F bar point to the objects of the same types. And to field heap abstraction, MAHONG only merges type-consistent objects. Let's use this example to help illustrate this concept. Suppose we focus on objects O1 and O2. And these two graphs shows the objects reach from O1 and O2 through field access. We call them field points to graph. For example, this edge means that O1.F points to O3. And this table lists the types of objects pointed by all field sequence of O1 and O2. We can see every field for the types of objects pointed by every field sequence of O1 and O2 are the same. So as a result, by definition, we say O1 and O2 are type consistent objects, and they will be merged by merger. Then the next question is how to check type consistency. The naive brute force checking doesn't work, and our solution is to leverage sequential automata. We discovered that the problem of checking type consistency of objects is totally equivalent to the problem of testing the equivalence of automata. So to check type consistency of objects, our idea is to transfer it to this automata problem. And firstly, let's see the definition of sequential automata. We borrow this concept from category theory. And a sequential automata is a 6-tuple, which is more general than the traditional 5-tuple automata used in compiler techniques. And the first 4 elements of both automata, namely a set of states, a set of input symbols, the next state map, and initial state are totally the same. And the set of final states in the traditional automata is replaced by a set of output symbols and output map in sequential automata. Now let's see how these two problems are connected. And our key insight is that we found an object and its field points to graph can be perfectly mapped to an automata. So after we map objects to automata, we can connect these two problems. Let's use this field points to graph of object O2 to see how we map the object, how we map it to an automata. Firstly, these objects are mapped to the state in an automata, and the field names are mapped to input symbols. Then field points to map correspond to the next state map. And for an object O, field points to map store the objects pointed by its field. And for a state in an automata, the next state map stores its next state after reading certain input symbols. Then the object to be checked corresponds to the initial state of automata. For this case, is O2. Then the types of these objects are mapped to the output symbols in the automata. Finally, the object to type map, which map each object to its type, are corresponding to the output map in the automata. And after building this mapping from objects to automata, we can now transfer the problem of checking type consistency of objects to the problem of testing the equivalence of automata. So the next question will be how to test equivalence of automata. Our solution is to leverage the Hopcroft-Karp algorithm with minor modifications. And this classic algorithm is almost linear and is very efficient. And now let's see our methodology. This is our will and workflow of our MAHONG framework, and this is MAHONG. Generally, it obtains field points to graph from a pre-analysis. Normally, it is fast but imprecise points to analysis, and each point to analysis can output field points to graph. And it will build a new heap abstraction to make points to analysis. Normally, it is precise but expensive analysis. MAHONG itself contains 4 components, and it enumerates pairwisely all the objects of the same type in field points to graph. And it uses an FA builder and DFA converter to map these objects to the automata, which will be given to the equivalence checker. Then the checker outputs the equivalence of the input automata. Based on this equivalence, heap modeler merge type consistent objects to build a new heap abstraction, which will be given to a later precise points to analysis. When working with points to analysis, Original allocation-site heap abstraction creates one object for each allocation site. And our margin heap abstraction creates one object for each set of type-consistent objects to avoid heap over partition. We have implemented margin in Java. It contains only 1,500 lines of code in total. It has been integrated with Heap. And margin can also be easily integrated to other point analysis frameworks. Now let's see the experimental results. We want to answer two research questions. The first one is about margin's effectiveness as a pre-analysis, and the second one is about margin-based point analysis. Firstly, we want to see whether margin is lightweight for large programs and whether it can avoid heap over partition. For efficiency, this table gives the pre-analysis time, which consists of three parts. CI for context intensity points to analysis, FPG for reading field points to graph, and margin for margin itself, which checks automata equivalence and field heap abstraction. And these numbers are seconds. So in total, the pre-analysis time for each program is only about 1 minute on average, and margin itself spends only 3.8 seconds on average. And this is benefit from our automata solution. So it shows that margin is very efficient. For heap partition, we compare the number of objects created by allocation-site abstraction and margin. And the longer bars are allocation-site abstraction, and the shorter bars denote margin. And by merging type-consistent objects, margin significantly reduced the number of objects by 62% to avoid heap over partition. And it's time to see margin-based points analysis. We want to evaluate whether margin can accelerate points analysis while preserving the precision for type-dependent clients. We evaluate these 5 different mainstream context-sensitive point analysis provided by Heap, and they cover 3 different kinds of context sensitivity. And time budget is 5 hours. We use these 3 type-dependent clients, and the details contains too many numbers. So here I just show some summarized results. And for the most precise analysis, we use namely 3 object sensitive analysis. Margin achieved the speed up of 131 times. At the same time, for core graph and devirtualization, margin only causes very small precision loss, and it can even totally preserve the precision for method casting. And for all the points analysis we use, margin achieved the speed up of average speed up of 50 times. And again, it only causes negligible precision loss. Particularly for these 5 programs, when they are analyzed by 3 object sensitive analysis, the most precise one we use, with a margin, the analysis is unscalable for all of them within 5 hours. But with margin, the analysis can finish within from 1 minute to 84 minutes for this program, and the average analysis time is 33 minutes. So these results demonstrate that margin clearly meets our goal. It can significantly improve the efficiency of different points analysis while preserving almost the same precision for type-dependent clients. As a direct impact, margin can benefit many program analysis where the core graphs are required. Thank you.
So we have time for some questions. The thought of the biggest part, can you say anything about the size of the alphabet that you get? How many fields?
We have such numbers. In paper, I think the average is about 1 to 2,000 fields each program. So that's the size of our alphabet.
So what sort of things cause you to lose this? Is this like when you're checking instance equality of objects or something else? Because it seems like if things are typed in system, then you would lose no precision.
We lose precision because of the imprecision introduced by pre-analysis. For example, we have some example for this, some slides for this. So, for example, in a pre-analysis, the pointful analysis reports that these two objects point to O1 points to this object through this field, but this can be false positive because if you use a more precise pointful analysis, and maybe O1 or OA only points to O1 and OB only points to O2 in the program. So this may introduce some imprecision to our marker due to the imprecision introduced by pre-analysis.
So actually, I have a question about this. So I don't understand the semantics of this sequential automata because non-determinism in classical automata is basically disjunctive. It's saying that if you have multiple paths and one says true, the other one says false, you accept the word.
Yeah.
So there isn't a distinction between like things I accept and things I don't accept, and every run has the same label. So in your case, you have these labels on each state, but non-determinism can cause you to have two labels for the same word. So what is even determinization here? Is it the join of this type?
I think this is the reason why we need sequential automata instead of the traditional automata, because traditional automata only output accept or reject. But to solve our type consistent problem, we need to know their types. So there could be A, B, C, D, or any.
I understand,
types.
but if you have two non-deterministic runs, one that comes with state with label A and one with label B, what is the deterministic of
I see. So so you are talking about an F-ray, right?
Yeah.
So in our sequential automata, when we finally stop at different multiple states, the output is the map this state to their corresponding output symbols. So that's a set of output symbols. So that's our result. It's output.
So in the deterministic automata, you have the set semantics.
Yeah,
so each state has a set of types.
Yeah, its output is set of output symbols.
Okay.
Types.
Okay, thank you.
Thank you.
There are other questions. Actually, we have 2 minutes. So I would have actually a suggestion. You don't need to actually determinize the automata to check equivalence. You can just run off from card on the non-deterministic automata. And there is a way to do it very efficiently. There is a Focus 13 paper by MAHONG and Heap about how to do it.
Sorry, I don't really understand.
So you don't have actually to determinize to check equivalence?
Yeah, we don't actually run on the automata, but we need to test. We just represent this problem on the form of automata and we test their equivalence. So we did not actually run on this automata.
Okay. Let's thank the speaker again.